Okay, welcome to a new chapter. We're looking at lecture 36, chapter 9, section 1. We're going to be talking about pressure. All right, so first off, a quick reminder about what a gas is. Now, a gas is, just a collection of widely separated particles. Okay, very widely separated. There's a lot of space in between them. So they always, any gas, I should say, not the particles, but the gas will expand to fill its container. Okay. So you start out with your gas particles down here in the corner. They will go out in all directions because there's nothing to stop them until they fill their container. So your typical gas has no shape and no volume. Okay. So, what is pressure? Well, pressure technically is force over area. So, force, you apply a force to an object will accelerate. Okay? You apply it over an area, okay? Then you have pressure. You're exerting pressure. So, same force over small area is a lot of pressure. Okay, think someone stepping on you in high heels. Force over a large area, that would be far less painful. Think snowshoes. Okay. And that's why snowshoes function the way they do. It's because they take your weight, they spread it out over a much larger area, so it's just easier for you to move through the snow. Okay. So that is pressure. Pressure is force over area. Just any sort of force over any sort of area. Now, what are the units? Officially, in terms of SI, the units of pressure are the Pascal. Okay, that's newtons per square meter. So that is to say, okay, we're talking about Newton would be about the weight of an apple. And a square meter is, a square 1 meter on a side, so that's top of a washing machine. So you put an apple on top of a washing machine, you've increased the pressure by 1 Pascal. That is a very small amount of pressure. Okay. Which is why, when we're doing practical sort of work, we tend to use atmospheres, okay, where 1 atmosphere of pressure is equal to 101,325 pascals, or 101.325 kilopascals. Okay, so that is the average pressure exerted by Earth's atmosphere at sea level is 101,325 pascals. We don't notice it because we're always surrounded by the atmosphere. So it's constantly pressing on us, and it's just we're used to it. Take it away, and you'd notice pretty darn quick. Another unit is the bar, such that 1 bar is equal to 100,000 pascals. It's a rounder number, makes it easier to convert to and from pascals, and it's pretty close to atmospheres. Here in the U.S., weather services tend to report in bars or in millibars. Okay? So a millibar being 1/1000th of a bar. So 1,000 millibars equals 1 bar. Equals 100,000 pascals. So 1 millibar, it would be 100 pascals. Okay. Thus on, weather maps, you see those lines. and they'll say low and high, referring to air pressure. Those are called isobars. Okay? They're talking about a line of equal pressure. Okay, so those are the units. We typically use atmospheres when we're talking about gases and gas pressures, unless we are dealing with particular circumstances. You will often also see pressure reported in millimeters of mercury or inches of mercury or torr. This is a kind of a historical thing, referring to how pressure, once upon a time, was commonly measured. We'll talk about that in a bit. Inches of inches of mercury, who cares? But 1 torr, named after dead Italian, Torricelli, is equal to 1 millimeter of mercury, and 1 atmosphere equals 760 millimeters of mercury. So at atmospheric pressure, you're going to have a pressure of 760 millimeters of mercury. Now let's go ahead and talk about that historical circumstance. Specifically, we're talking about a manometer or a barometer. Once again, you see bar referring to pressure. Okay, so if you were to take a tube closed at one end, open at the other, and you fill it up with mercury, and then you cap it off, not with your thumb. Your thumb can't hold that much mercury, and you upend it in a basin full of mercury. Okay, so mercury in the basin, mercury in the tube. What's going to happen is the mercury will fall partway down the tube, leaving a vacuum up top, and this down here would be mercury. And it stops at some point. Okay? And what has happened is that you have air pressure, atmospheric pressure, pushing down on the mercury in the basin, and you have the weight of the mercury in the tube pushing down as well. The height that the mercury is held at is where the mass of the mercury times Earth's gravity is equal to the force of air pressure, basically. See, so times the height. There we go. It's equal to pressure. So when those two forces are equal and opposite is what I'm trying to say here. That is what holds the mercury at that height inside the tube. And at typical conditions, that height is 760 millimeters. Why do we use mercury? Because under normal atmospheric conditions, air pressure can hold up approximately 34 feet of water. So it would be ill-advised to try and construct a manometer out of, a tube full of water, because it would have to be 34 feet tall. That's more than a story tall. So mercury is much more useful for that, just generally speaking. And once upon a time, that was how you constructed a device to measure air pressure. Was you had something holding just a tube of mercury in it, which is not the best thing in the world because mercury is kind of toxic and will drive you insane. So nowadays we have other devices that we use, but they all go by these names here, manometer or barometer, and they just are a way to measure air pressure. Okay, so those are what we are, that's all we need to talk about for pressure. Pressure is force over area, B equals F over A, and that is important. That will help you a lot when we get to kinetic molecular theory. And 1 atmosphere is equal to 101,325 pascals, is equal to 760 millimeters of mercury, is equal to 760 torr. And those are your units for pressure. Okay, in the next lecture, we'll start talking about the gas laws.